Hi, we're a group of students from UCL Computer Science who worked with a Japanese student from the NII in Tokyo on a project concerning TfL's Barclays cycle hire. As you can see, the scheme covers a large area of central London and is always in high demand. The problem we address in this project is the failure of meeting this high demand. Firstly, customers require an empty dock when they arrive at a station in order to park their bicycle. Secondly, customers expect a docking station to provide a bicycle when they require one. Not meeting either of these demands will lead to a loss of customers. Our solution aims to minimize this. We want to help TfL in efficiently allocating bicycles. TfL would benefit from an increased efficiency and reduced costs. Users would benefit from a higher availability. The challenges we faced were that we did not have access to historical data and the inherent difficulty of data modeling. Some of the assumptions that we made during this project were that the weather and TfL APIs were reliable, the number of bikes were consistent, and that the stations were functional.
The infrastructure of our system is composed of 4 layers to model raw data into useful information consumed by users. The data is fetched from external sources like the TfL API and stored into a local database. Computations are run against it and results are saved in the database. Then the data is streamed to our users in real time. The algorithm is based on a spatio-temporal network that runs on data collected in the database. In short intervals of time, up to 2 hours, the difference in the number of bikes at a station is measured and a correlation is created with respect to the weather. Here, we have a station represented by a red dot and 3 other stations that are correlated to it represented by green dots. When new data comes in, it triggers the connections, which the system then uses to build forecasts. As we can see, if 5 bikes leave the red station, we expect to get 2, 2 and 1 respectively in the 3 green stations that are linked with the first one. The prediction for a station consists of an integer. A positive integer represents the surplus of bikes that need to be removed. A negative integer represents the deficit of bikes that need to be added. We went for an iterative process and looked for feedback as a means of evaluating and improving our designs. Ultimately, our goal was to create a simplistic design for TfL workers to use effectively. We researched various different APIs in order to generate the data visualizations and chose to go ahead with Google Maps. The feedback from our team as well as our clients revealed that we should also show specific information about each docking station. This information was displayed in the form of a list specifying the number of bikes in each dock that should be either added or removed. We also experimented with different color themes for our designs to ensure familiarity and consistency with real-world conventions.
So let's see our system in action. Let's consider a scenario where Jeffrey is a TfL employee and his job is either to remove bikes from docks or add bikes to docks. Judith is another employee who works at the offices of TfL and is using our system. Judith sees that the docking station at Moorfields in Moorgate needs 12 bikes removed, and Jeffrey happens to be the driver closest to this particular docking station. Judith notifies Jeffrey about the situation. Jeffrey acknowledges the message and proceeds to the docking station to remove 12 bikes. Jeffrey arrives at the docking station and checks the app on his mobile device, and it just so happens that during his travel to the docking station, the original value of 12 has now changed to 10. Jeffrey then proceeds to remove 10 bikes from the docking station.
As you can see, we have combined sophisticated data visualization and spatio-temporal networking algorithms to create our system. Our system is an accurate and robust optimization tool with the potential to have a significant impact on the way TfL allocates its bikes.